Okay, so for record, all of the students are here. Go to attendance, not all present. Okay. Now all of you can hear me, right?
Yes, sir.
Okay. All right. I'm showing my slide now. Let me know if you're not able to see the PowerPoint slide now. Okay. Today we're going to look at your tutorial question, chapter 2, question 45. Right? Question 45. For the first session, we're going to look at question 45, for 46, and then 47. If we have time, we go to 48 or 49. Yeah, so these two, if you're not able to cover, then I will still give you the answer in my PowerPoint slide. Then you can go and look at it for your own revision. Okay, so for question 45, we're going to look at mechanical energy equation and Bernoulli equation. So we're going to look at what is the similarity between these two, and then what are the modifications we can done by using either of them. Okay. Now for the following slides, you don't need to copy because later on the answer will be given to you in my PowerPoint slides. So for the next like 10 minutes, you just look at the screen, and then if you have any question, just ask me. Stop me if you're not able to follow. So for the next 10 minutes, what we're trying to do is that we try to understand how mechanical energy and Bernoulli equation they can combine, or they can make comparison. Then we see what is the difference when we apply them. Okay, right. So we start with the mechanical energy equation. So this is the equation that we use, that we see present to you for the last few days ago. Even this last Tuesday, we look at this equation. So what does this equation tell you is that all these are energy that we can calculate for a system. All right. So we have a m dot means mass flow rate, and then this one is the internal energy, kinetic energy, potential energy, and this one is the pressure component we derived from the previous equation. On the right hand side, this one is our power, or our product or reaction from our force and torque. So this one is our heat transfer rate. This one, heat transfer rate. This one is the power, right? Our work, the rate of change of our work. So this side is more on the event that we can see, or the output that you can see. And on the left hand side is more on the energy that we have available for us to transfer from the left hand side to the right hand side. Okay, and yeah, so 1 and 2 is just the output and output. 1 is for input, 2 is for output, or location 1 for in, and location 2 for where the energy arrives. All right, now what happens if we have a steady flow and the flow is compressible? Right, now before we go for that, so if we have a control volume for our mechanical energy equation, if the flow is steady throughout the control volume, then power for the shaft. Mean we don't have work on the shaft itself, right? And then when we have an incompressible statement in our question, mean that in this equation all our density will be the same, right? It just means that our density will be the same when we see the word incompressible, right? Don't put as a 0, so there is a value for density. And then yeah, this is just when we simplify for steady and incompressible condition, where the first equation we see here, we change all the denomination 2 and 1 into the same uniform general density here. Okay, and we take out the power from the shaft. There's no power from the shaft when we have a steady flow here. And then the next line here is that when we want to calculate our parameter in the unit of mass, when we Okay, so this one, when we divide the whole equation with m dot, including we take our heat transfer rate on the right hand side, we divide with the m dot, we get a small q net, means our heat transfer here, and then this one all are in the unit of mass, per unit mass. Okay, so this is the equation when we take out the m dot on both sides. Then we need to rearrange this equation so that we can make comparison with the Bernoulli equation. So up to this stage, we're still looking at the mechanical energy equation, and then we put into the structure that allow us to compare with the Bernoulli equation later. So we put the all the outlet or output component on the left hand side. We put all the P2, V2, and Z2 on the left hand side, and then we put all the inlet or station 1 or section 1 component on the right hand side, right? So it's just a rearrange of our equation just now. Then we pull out the Bernoulli equation. So this is the Bernoulli equation that you've seen in the introduction to fluid mechanics. When you calculate the energy, when the flow from one elevation to another elevation, this is the equation that we use when we have a fluid. So we have a P2 rho V2 square divided by 2, and a specific density times our elevation left. Also, I think there's a typo error here. All right, so just take note that later on I'll make adjustment on the slide. So this actually is 1. This is 1. This is 1. So, all right. So, what is happen on the output? Same with the inlet. So 2 equal to 1. Right. So this is the structure of the Bernoulli equation. Then we make comparison just now, right? We make comparison between these two. So when you compare these two, you can, at this moment, our energy equation was still not same as our Bernoulli equation. So we need to make our energy equation in this form. Meaning, look at the first one, we need to get this form into a P2. So we need to times the whole equation with the rho. So we take out the density in the energy equation. So it means we times the left hand side and right hand side with the rho. All right. Or you can, so this is we use a Bernoulli instead. So we take the Bernoulli equation, divide by density, means yeah, we still see the same structure so that we can make comparison. So just now what I explained is that I use energy equation to compare Bernoulli. But on this slide, when I prepare these slides, I use a Bernoulli equation to compare with energy. So I take the Bernoulli equation, I divide with density. So left hand side, right hand side also same. So all the term inside this equation with the density. All right. So this specific density converted after we times the density, we get only gravity acceleration. So the third equation that you see on the slide now, this is called Bernoulli equation in energy form. Means what we see here is a Bernoulli equation in the shape of the equation, in the shape of energy equation, so that we can compare what we see here with this one. So we can make direct comparison between the top and bottom. Okay. Right. Now, if you make a direct comparison, the difference is only the back one, this one. All right. The energy equation have something on the back, this one. Okay. So meaning if you direct compare this one and this one equal to 0. This term, whole term at the back here equal to 0. All right. And again, we have to remind ourselves, what is the equation that allow us to put the whole thing, the last term that I show to you right now, this one equal to 0, is that when we have a steady incompressible flow in the frictionless condition, means the flow inside a pipe, a tube, without friction, right? Then if your apparatus or your test tube that have a friction, then you have something on the back here, right? You have a positive value for this term here. Okay, so at this point you should able to see what is energy equation and what is the Bernoulli equation. What is the difference, right? So we make a direct comparison here. We see that the term in the energy equation here equal to 0, and when we apply this one equal to 0 is when the system we have is incompressible flow without friction. Right? Of course, when you go to work later on, or when you done your research in your final year project later on, this component cannot be 0, right? You need to get some value from your calculation later on. Right? All right. Now, when we look at the Bernoulli equation in energy form, this 1, 2, 3, this term combination of these three, we call it useful energy, which means that energy that we can use to generate something. Either is to generate our turbine, or to generate our pump, or to do something work, or can do for heat transfer, right? So this is a useful energy. So if you compare the energy equation, the last term here means we will have a loss of energy. We have a loss of energy here. Means we have a total useful energy minus what is our input, and then these two must be balanced. This left hand side, right hand side must be balanced. So this number is bigger than this one, so we need some loss component here. So you minus the loss, you get the balance equation here. Right? So far there's no complicated component here. It's just some understanding what is mechanical energy equation and a Bernoulli equation. What does all these thing means when we want to apply them? Okay, so right, so energy equation we can just write in the very simple term, like the last one we always minus the loss. So again, this equation very important. It's going to be in your coming test one scope lah. So just let you know. All right. So we have clear for question 45, and then we further look at the equation. What happen if we have certain statement in the question later on? So when you have incompressible, yes.
If I'm to ask, like, if you go back to the previous slide.
Which one? This one.
Yeah. And
okay.
Then, you see, there's rho v2 over v2 squared over 2. Which type of energy is that? Like? Because the Gz2 is potential energy.
Again, I cannot hear very clearly what you say. Can you repeat your question?
I was trying to identify the type of energy, the useful energy, which energies are. Is it like potential, kinetic, kind of stuff like that?
Oh, you mean what does all this mean, right? So yes, in energy that we know the energy we consist of kinetic energy, potential energy, and internet energy, and the pressure component also. So in this slide, it just show you that which component is a useful energy and which component we consider as a loss when we want to use them in our scenario later on. You asked about V2, this one, right? So yes, this is a kinetic energy. Do I clear your question?
Yes. And G2 is potential.
No, this component is, if you refer back to the original equation, this our potential energy, right? If you have a rock fall from the certain height, right? Let's say you throw a rock from a certain height with the m. M is the mass of the rock. So the kinetic energy at this point will be equal, potential energy at this point will be mgh. It will equal to this equation, right? So of course this is referred to a position, and under the effect of gravity and the height. So we get this one, right? So we already take out the mass in this equation already, right? And kinetic energy, the original equation is half mv square. This is the original kinetic energy equation. Again, we take out the mass in this equation already.
Okay.
Yeah. So because this whole thing is something, the unit divided by mass per kilo. All this term is in per kilogram. The unit in for this equation, right? Just let you know. All right. Yeah. Any more question before we move to the next slide? Right. Just now we stopped at here. All right. Now this is the original equation that we see before we take out the mass. So this whole thing, this is a very important equation that we derived, I think, last Tuesday. This equation is very useful when you want to solve mechanical energy equation. We want to solve the when you deal with energy, right? The energy will transfer to heat transfer and also mechanical work. So this equation will define the total system. And then we will simplify when looking at the statement, right? So yep. So this one is just to tell you that what look back at our mechanical energy equation. We divide our left hand side, right hand side with our mass dot. So it just changed some denotation. So capital Q dot will become a small q, means all of these will already divide by m dot. This is just a mathematics arrangement. All right, so we rearrange back to Bernoulli just now, just to compare what happened between them. Again, we prove that we have a loss behind our equation. Right, this slide just show you that we can conclude what happened in our mechanical energy equation can become a loss, just a general term for these three, right? Yep. And this equation in this slide later on will be known as mechanical energy equation or extended Bernoulli equation, because this equation, this term we look at because we compare with Bernoulli equation. All right. So yep. So just take some note on this, that when a question asks you to solve a certain problem with extended Bernoulli equation or with mechanical energy equation, then you know that this is the equation that you're being instructed to use. All right. Yeah. So as a summary for question 45, so what you see on the question 45, under there is an equation there. So that equation is called mechanical energy equation. Right. So for the past like 15 minutes just now, is more on the derivation, right? More on the derivation, how we arrive and all this. Okay. Any question before we move to 46? All right. So all this will be my slides. So you just need to go back to the slides for your revision later on. Again, there's a typo error just now. On one of the slide, yeah. Yeah, this one. This one is wrong. Left is denoted by 2. Right is all denoted by 1. So it will be balanced from the input and output. Okay. Now we try to look at a few things with this question 46. So for example, sometimes your boss or your client or your customer just provide you some spec that in terms of, for example, specific weight, or in the component itself, the component that used to pump water, then in the spec itself you'll see work head HS or head loss HL, total head, and all this in the component spec sheet. So you need to know that how to calculate whether it is operatable or not. All right. Now, just now we have the equation that you see on the slide there. So, okay, so just make a small correction in question 45. Question 45, especially the work for the shaft. The one that I use in the tutorial question is what you see on your tutorial slide. I use capital W with the dot shaft. All right. There's a typo error, so this is wrong. Is without the dot, because this equation we already take out the m dot already. Right, just make a note in your tutorial there. Okay, now we multiply with density. We just try to modify this one. Then you'll get an equation that involves with energy per unit mass. Then you use this equation. All right, this equation, when you times the density, then all of these will be in energy per unit mass. Then what happens if the question that's only give you shaft work head HS or head loss head and all this, then you can modify further, right? So meaning you divide this equation again with gravity G. All right, the whole thing with gravity. Then you'll get this equation. Okay, so this is just some application when how you transform one equation to another one, depending on the question that you see, right? So this is just application. Okay, this is what we see just now from this equation. So our HL is we take our loss divided by G by relationship where we done just now, and HS is our work from the shaft divided by G, and this is a small w, means is a work per unit mass, means per kilogram, divided by your acceleration of gravity. This is not the kilogram gram. This is the gravity acceleration, G. Right. So and then you can. This is just a mathematics relationship with how you transform from small w into w dot, which is power in this form, and this one back to in the term of a specific weight. These just all these are mathematics relationship, right? So what is important is what is the application of HS in real life. So for turbine, you will see in the spec sheet or turbine specification, you will see your HS normally will be negative some joule per kilogram or so on. So when the shaft work done by the fluid means the fluid will push the turbine to work, then you will get a negative. Then for the pump, it will be a positive when the fluid is done on the pump itself. So this is the difference between turbine and pump. So when you get negative for pump is for the turbine scenario, then this is the meaning of the value. For example, you get HS equal to negative 50 joule per kilogram. Then it means that the fluid is doing something on the shaft. Right? It means the fluid is pushing the shaft to turn inside the turbine. Okay? Then if it's positive, then it means that you are using a pump. Right? So this is just some conversion when we want to use the energy equation in a different scenario. Right? So in this case, you see an so in this case, just general. So you can substitute the value with the positive, negative when you use either turbine or pump. Then we look at the example. Then you'll see what is all these equation mean come to meaning. Yep, some detonation, some meanings. Means on the left hand side, all the output, the pressure, velocity, and elevation, you combine the energy. On the left hand side, it will call a total head, means H, capital H. And yeah. And then the left hand side, or this one is also total head for section 1. This is total head for section 2, right? Plus HS minus HL. So this is the simplification of energy equation in terms of head. This term head is
the small, the HS and HL.
Yeah, this is just given by this one, right? So HS just now we derive from this equation. We take our loss and then we divide with gravity. Then we get HS and HL. Then if you want to look into more detail, it means that HL is, you take all the loss divided by acceleration of gravity, you get HL. HS, it means you take the work done by the shaft divided by gravity. Then you get HS and HL. Okay. All these are derived from mechanical energy equation. All right, by looking at these slides. Do I clear your question?
Yeah. It means
Okay.
the HL is what is the meaning of HL, HS?
Yeah. We'll look at one example, then you'll know what is HL and all this. It's just a term in fluid mechanics. It's just a term in fluid mechanics that represent what is loss. For example, if you let's say you have a pump, you want to pump water to a certain height, right? So this is called head also. Means it's a distance that can travel by the water or by the fluid or by the element. It's just a calling to represent the energy, right? We will look at example, then you will know. It's just a name to represent this entity. Okay, let's look at an example, then you will know what is head and all this. Okay, now we'll look at question 47 now on application of mechanical energy equation and Bernoulli equation, especially on the mechanical energy equation. So let's say you are given a diagram here. So the air flow from a room left to right. This is on the room on the left with different vent configuration. you have one cylindrical hole, which means you drill the wall with a cylindrical drill. The second one with a bit chamfer here, with a bit rounded corner here. So you have a 2 hole on the wall. So we want to see what is the volume flow rates between the first one and second one. Right. So we have for the first one we have 120 mm, and the second one also 120 mm. Only difference is the entrance from the left hand side. Right. Room pressure held at constant at 1 kilopascal above atmospheric pressure. Yeah, both vents exit into atmosphere. Given the loss available energy associated with the flow through cylindrical vent to the room exit is given by this equation, 0.5 V squared divided by 2, and another one is given by 0.005 V2 squared divided by 2. Both are uniformly distributed. Right? So this equation that you see in the statement here is to represent the loss, right, in the transfer. Okay. So when you have 2 holes and then we want to see compare the volume flow rates. This is our Q in these two cases. So straight away we jump into the question. So again we look at the control volume. Right, we're still under control volume chapter. So in your tutorial sheet there already given the control volume. On the top is a sharp corner, sub entrance. Second one is more on the chamfer, more rounded entrance. All right. And we focus on the main parameter in the question. So we are going to look at volume flow rates. It is Q. So we know that Q equal to velocity times area. So the question asks us to find the volume flow rates compared to 1 and 2. Why we use the section 2 velocity? Because this is the one that we can calculate. And V1 here is not given. Right? In here, it give you equal to 0 because the area is too big. So in general, you can see that the flow actually not moving because on the left hand side, the area is too big already, right? And we match whatever we know from the question. So again, call the mechanical energy equation, right? Write this equation in the space given there. All right. First thing is you focus on the volume flow rates, which is given by Q. Q equal to V times A. So even in your exam, you don't know how to write the denotation. You just write A times V. We given that V equal, you write V equal to velocity, A equal to area. Then you write this equation, right? You'll get some marks for in your answer. Although you in this statement you didn't write the V2 or V1, right? As long as you show your understanding what is the volume flow rate definition, then you'll get some effort marks for your understanding. Okay. But again, this module is easy to score as long as you know what we are looking for. All right. So again, write the mechanical energy equation, which is P divided by rho plus velocity square divided by 2 plus gravity acceleration times the elevation. Then the right hand side, you copy the same, only change it to input or inlet 1, and then plus the shaft work minus the loss. Right. This equation is on the application of a mechanical energy equation. So you copy this equation, then later we will dissect the question accordingly. Right, and we start to solve already. All right. Now V1 equal to 0. although in the question it do not say anything about V1, if you have a very large space in front of the inlet, very large space, the way that you see on the velocity, the input into that one, we will put as 0. It will same as when you have water from the dam, and then the water flow from one end to another end. So your water flow in. So what you see from here, the velocity from this horizon here, let's say V1 here, you will see that the water actually sink very, very slowly. If you have a very large dam here, the water will flow, will drop very, very slow because the dam is so big. So it will the same concept apply here also, right? That's why we have it become 0. So this one you need to write when we ask the same similar question in the exam later on. So you need to write this one out. This one also will give you some marks. And then no elevation means you see that from this point inlet to outlet, actually there's no change of elevation. It's the same for two case. So case 1, input here, out here, so elevation same. So Z2 minus Z1 equals 0 mean if you put your Z2 proof from the left hand side to the right hand side, you will get 0 later on. So these are the basic understanding before we try to solve for the parameter. Right? Yes.
So V1 is 0 for both diagrams, for both scenarios.
Yes, because this is one scenario. This is one scenario. So both have the same input where we come from a very big room. The flow come from a very big room. So I explained about the effect when we have the very big room and then you go into a small chamber, something like that. Then your velocity will assume as 0. This is a simplification steps when we have a setting like this. All right. So this is the reason why we put equal to 0. All right. Do I clear the question?
Yes, sir.
Okay, good. Right. The second one is that yeah, we cancel out these two because when we move, you move the right hand side left to right, you'll get G, and then Z2 minus Z1. Because we know that there's no change of elevation, this term will become 0. So that's why we can cancel this one. All right. Okay. Then because we don't have shaft component inside our system, because we don't have shaft, we don't see any shaft, any working, rotating object here, then we can further simplify our mechanical energy equation. You take out the shaft component. Right, this is so direct, so sometimes there is a free mark inside the question, so you need to know for how to take out and then how to simplify it. So at the end, you will get a very simple equation. Right. So at the end, we arrive at a very simple equation like that. So from a very lengthy equation, because of the V1 equal to 0, because there's no elevation between input and output, because there's no shaft inside our system, we take out 1, 2, 3, 4 terms inside the mechanical energy equation, cancel out, and then rearrange the equation so that it become more tidy, right? So P2 divided by rho plus V2 square divided by 2 equal to P1 divided by rho minus loss. And these two laws are given in the question, in the statement, right? In the equation form. So for the first case, here for the first case here in the statement was given the loss equal to 0.5 V square 2 divided by 2. Second case given in the statement is loss at for the case number 2 is given 0.05 V squared 2 divided by 2. So you just need to substitute inside and then you see what is the equation, right? So again, this is just a side note for the structure of this equation. So both of these are in term of in the form of k with a constant value v squared divided by 2. So we can put this equation in this general form, meaning we modify a little bit our mechanical energy equation into this form. So we have P2 divided by rho plus V2 square divided by 2 equal to P1 divided by rho minus KV square divided by 2. Right? And then we want to find our velocity here. Why we want to go for velocity here? Because again, we need to focus Q equal to VA. We want to find this term because just now we define our Q equal to V2A2. So A2 you can calculate. We already have this term already. We want to find this one. We still don't know what is this. So from mechanical energy equation, we rearrange this one in V2 equal to what? Then we substitute inside here, we get our Q. This is a total, this is what we're trying to do for the next 2 or 3 slides. Okay, so you rearrange the velocity from the equation above this one. You get square root of P1 minus P2 plus 1 plus K divided by 2. Right. So this is how we get our V2. So again, our Q equal to V2 times your area. So this is just a conversion from what we have in the diagram. Change our A in terms of diameter, pi d squared divided by 4, or we can straight away use pi r squared, r2 squared, right? So when you do calculation, when you give your answer, please give a very specific answer, right? So so in the exam, don't skip the conversion. Don't skip these steps. You need to write how you get the area and then give your answer, because sometimes from this step to this step, there are some hidden marks to help you. All right. So you substitute all the value. This is just a reference value. So you get your volume flow rates for case 1. You'll get 0.445 meter cube per second. And then your Q2 for scenario number 2, you'll get 0.372 meter cube per second. All right, so this is how we apply the mechanical energy equation in this scenario. All right, so far I don't see any complicated things here. Any question you want to ask me? Try to understand the solving strategies that we try to involve here. Right. At first, we pull out the mechanical energy, and then we have all the statement. We simplify the equation. At the end, we arrive at a very simple equation. Yes. Yeah. What's your question?
So about K, is K a constant or it's given in the equation?
Which one?
K.
Oh, now in this case, I try to put everything in general equation. You can substitute by one. You can do it very in the in the more what I say, in the more slower steps, mean that you can do for, okay, you can write scenario situation 1, then you write P2 divided by rho plus V2 square divided by 2 plus not plus, equal P1 divided by rho minus 0.5 V square divided by 2. Then you can rearrange this one. All right. You rearrange this one, you get what is your V2. From this one, you substitute all the value that you know. All right. Then you get what is your V2. Then you substitute your V2 in Q equal to V2A2. Then you still get 0.445. Okay, after you done the first one, you go for the second one, situation 2. Repeat this process by substituting 0.05 V2 square in the loss component. Then repeat the process, you'll get, for the second scenario, you'll get V2 equal to something value, and then you substitute V in the second scenario, you will get 0.372 meter square per meter cube per second. You can do it both way, either way.
So that case we have to
This
take
one.
it from the V.
Which mean
How do you get?
no, this one is because we look at the form here, we transfer into a general equation. We look at the structure of the equation, we transform in the very general equation here. So later on, when you substitute this one, you just look at your k. So your k have two value, k equal to 0.5 for case 1, k equal to 0.05 for case 2. So you substitute this one into V2 equation. You understand?
Yes, but so where do you get 0.5 and 0.05?
What does the question tell you?
The question?
The statement here? You see?
Okay.
Given the loss in the variable, if you look at your tutorial question, is in the last line, the last fourth line, if you count from the last line on the question. Yeah, the statement is given there. So how we get the 0.5 and 0.05 is from here, from this statement. Given the loss equal to 0.5, this one. And then another one for second case equal to 0.05 V2 squared divided by 2. This is given in the statement. Are you able to link up? Are you able to?
What?
Again?
I got it, sir.
Okay, good. All right, so anyone have any more question on this one? No question. I will let you go and read the slide later on for question 48. Or you want me to explain? Because now it's 3:20. Yeah. If you want, I can go very fast for question 48. And then 49, go and look at yourself. What do you guys think? When we go through question 48?
Yeah, I can go on.
I can go through.
Yeah, so go through.
Okay, good. Okay, now I go very fast because the answer you can find in my slides later on. So again, it's an application of a mechanical energy equation. In this case, if you compare question 47 and 48, actually now you can see we cannot take out one of the term inside our equation. With this, we have a motto here. Right. So the axial flow means we have a fan. We will try to suck in some air from section 1 and then pull out from section 2. V0 equal to V1 equal to 0 again. I explained already because it's from the very large space and the velocity that we see from section 1, actually there's no change of velocity, right? So that's why I put 0 there. Huh? Okay. This understanding very important because when you try to solve for control volume and for energy equation later on. Okay. We have power given. Motor deliver 0.4 kilowatt power. Diameter given, the size given, speed given. Flow far upstream. Far upstream, what mean by upstream means that whatever on the left hand side means whatever on the section 1. Whatever that before the input means upstream. This is called upstream. This is called downstream. Right, apologies for my writing because I'm using mouse to write. Right, so just let you know that when you see upstream and downstream, it means that it's a different area, different zone that referring to. Okay. Right, now want to determine how much work the air have done. And we estimate the aerodynamic efficiency of this fan. So try to do how to solve this one. So again, you try to focus on the control volume. It is pull out all the control volume already given to you in the tutorial slides, in the tutorial paper. So all the area was highlighted, and this one do not included a motor. Right, focus on the main parameter, and then we match. So again, call the mechanical energy equation again. P2 divided by rho plus V squared divided by 2 plus G Z2. Z is elevation. And in this case, you know that there's no elevation again. All right. The flow from here, there's no change of elevation. So later on, you know how to simplify this one already. Right. And yeah. Okay. And if you use the rho in general term, means that we assume the flow is incompressible. Huh? That's a side note for this equation. Okay, then you have this equation already. Means you have the shaft work and minus the loss. So this is a complete mechanical energy equation that we try to use to solve this question. All right, start to solve already. Again, use the known value, which is V1 equal to 0. No elevation, you can take out the Z1, Z2. All right. We take out these two not because there's no value for gravitational acceleration, but because of there's no difference in your Z. Right. And all surfaces on both sides, which means 1 and 2, exposed to atmospheric pressure P atm on both sides, which means we don't have a difference. Delta P here equal to 0. Right. Delta P here equal to 0. Means we can take out the P1 and P2 component. So we only have a few components to solve. We simplify this lengthy mechanical equation into 1, 2, 3 terms only. All right. Now we rearrange the equation. We only have V square, V2 square divided by 2 equal to what happened to the work from the shaft minus loss. So again, this is from the energy, especially for the kinetic energy component. And just a side note in your tutorial there, 1 joule is a conversion. If you can, joule equal to Newton meter, means force times distance, Fs, or force times distance, right? Force and the distance traveled by a certain particles means you have energy already. So Newton meter, or another terms of joule equal to kilogram times meter square divided by s square. So you can do conversion. How you make the dimensional analysis? It means Newton equal to force, force equal to ma. So what is mass? Mass equal to kilogram. What is A? A is meter over second square. Meter is meter, so you get this term here. So if you take the force times meter, you get this unit. All right, so this is the conversion, right? So again, this one won't be given in the exam. You need to know how to convert from here because all the term that you use here is in unit SI, which is from this side. You need to know how to convert into this one or in this one. Okay, that's why I show this to you in the slide. Okay, remember to convert all the unit. So on the left hand side, you have 72 Newton meter per kilogram.
So,
Yeah.
what is I thought it would be like kilogram meter per second squared. What is like kilogram meter squared?
You mean this one?
Yeah.
I just explained just now.
Yeah.
Newton is what? Newton is the force, right?
Yeah.
Correct. What is the definition under second Newton law? Force equal to ma. Mass times acceleration. Correct?
Yeah.
Yeah. What is mass unit? Kilogram.
Kg.
What is acceleration unit?
M over a squared.
So this one you get kilogram times
M.
meter per second square. So in this one, 1 joule equal to 1 Newton meter. So you substitute what you get here. Newton equal 1 Newton equal to 1 kilogram meter over second cube over second square times meter. You get kilogram meter square. This one. This is in the dimensionless analysis we cover in the introduction of fluid already. Right? If no, then I don't know what happened in your previous module. Right? Oh, this one also in the physics also. Physics dimensional analysis to prove that the unit is correct. Right? So yeah, so do I clear your question on?
Yes.
Yeah, okay. So you need to have a strengthen your understanding in the conversion. So all these are from the fundamental understanding. Right. All right. Okay, let me clear the pen first. So on the left hand side, you get 72 Newton meter per kilogram after you do all the conversion. Right, you substitute the value of yeah, V2 there. V2 given is 12. Yep. Your velocity is 12. So 12 square divided by 2. 12 square is 144. Divided by 2, you get 72. Of course, here you get, in this term, here you get yeah. Okay. So we need to find the efficiency also. Efficiency, I think you learn in your static or dynamic class. So efficiency is what you take from the output divided by input. Means on the top here, you look at the useful work or useful energy divided by what you included inside the system, means total or your supplies, energy or work here. So we take something useful divided by total work. So we just expand what we understand on the efficiency definition. So useful work is shaft, because on the left hand side just now is a useful work, right? So we take the work shaft equal to loss minus loss, work shaft minus loss divided by our total input, which is what is in, right? So we need to recall what is our W shaft net. Means we take our power divided by m dot. W dot means power. Is rate of change of your work, W dot, divided by m dot. We recall what is m dot. M dot equal to rho AV or rho Q. You're going to see this equation many times for m dot. M dot equal to rho Q or rho AV. So A, you know lah, you just expand further based on the parameter given. Because in this case we have diameter, so we just expand a little bit this equation for the m dot, so that we can substitute inside there, right? And yeah, for standard air, you should know rho equal to 1.23 kilogram per meter cube. This for standard air at standard atmospheric pressure. So rho equal to 1.23 kilogram per meter cube. And yeah, power, recall again power. What is power? Power, 1 watt equal to 1 Newton meter per second. This is the definition of power. 1 watt equal to 1 Newton meter per second. All right. So you are given that in the statement, given that our system, our motor gives us 0.4 kilowatt of power. So it means that this is our power of the shaft in this equation. However, you need to change the kilowatt in the unit SI. Kilowatt equal to 1 kilowatt equal to 1 Newton meter per second. Then you substitute inside there, simplify your dimension. All right, again, you need to do all the conversion of your unit, put everything in unit SI, substitute all the value, you will get your power for your shaft. Sorry, I think this one don't have the dot there. Okay, don't have dot, don't have dot. W shaft. Okay, equal to 95.5, 95.8 Newton meter per kilogram. Typo error again. So this is how we use the energy equation to solve. Okay, question 49. I think I give you for your own revision. If you still don't know, don't understand what is question 49, then you can ask me during next class or during consultation hour or during a revision session before your exam. Okay. Also, you substitute in, you get the answer for efficiency is 0.75%. Right, n equal to 0.752 means you times 100, you get 75.2%. Means you put in 100 kilowatt, what you get is you get 75.2 kilowatt. Right, you put in like how many, you only get useful energy, you only get 75%. Okay. Right, so from this one, from the number itself, you should able to tell what does it mean, right? How you change this 0.752 into percentage. How many percent is useful power? How many percent is loss? And what are the source for the loss that you can think of inside the system? What take out the power or what take out the loss and all this, right? Most standard answer is friction, and also some, right? Because here it didn't mention any adiabatic process, so there may be some transfer energy into heat and all this. Okay, so this how it do. Okay, question 14. The last question, I will let you go and read the slides yourself. Huh? Okay, let me check. Okay, someone. Oh, Brian asked me a question. How many days is our exam? For your midterm test, only 1 hour, 2 questions. It will be evaluated. So 2 questions, and the component only 10 marks. Means you 2 questions, I will mark in 100%. I will convert it into 10% for the module, which means if you look into my slides on assessment, this one. Okay, let me stop the recording first.